Well, hello everybody. We are now on to chapter 19, on to the renal system. Probably my favorite physiological system because of how much total impact the kidneys have on the rest of the bodily systems. And the kidneys do lots of things. They just don't filter your blood, but they also secrete hormones as well. And they also maintain lots of things like blood osmolarity, acid-base balance. It's really amazing, especially when you consider that the kidneys, if you've seen them on a cadaver model, is they're pretty small. They're about the size of maybe a bar of soap. Yeah, as of right now, about 25% of your total blood is filtering through the kidneys. Each day, 180 liters of filtrate, a little bit more or less depending on your body size. But approximately 180 liters of blood plasma filter through your kidneys every day. And amazingly, that is all returned to your bloodstream except for about 1.5 liters that is used to excrete your waste products. That just shows you the amazing ability of the kidneys to not only filter your blood plasma, but to return it to your blood. And really, the kidneys are amazing. And we're going to be talking about the physiology behind them, as well as some of the anatomy as well. So let's get right to it. All right, so first we're going to talk about the functions of the renal system. It's very wide-reaching and broad, as I just mentioned. So the first is going to be regulates blood volume and blood pressure. So we're going to title this here, regulates blood volume and pressure. And what it does is it basically determines whether or not the filtrate that is, well, okay, instead of filtrate, let's use plasma. What it determines is that if the blood plasma that goes to the kidneys, whether or not it's returned to the bloodstream or excreted from the body. There is some variability there. Now, let's say that your blood pressure goes too low. Let's say that you have low blood pressure. What that's going to mean is that there's going to be more plasma returned to the blood. The inverse is true as well. If you have higher blood pressure, then you're going to have less plasma returned. There is a reflex that I didn't have a chance to talk about, but it's called the Frank-Starling reflex. I wish I could have talked about it, but we kind of glazed over chapter 15. Frank-Starling reflex. And what this basically means is that the more blood in the ventricles, the stronger the contraction. So if you want to increase blood pressure, one way to do that is to get the ventricles to contract harder, to produce more force, to increase the pressure of the blood flowing through your cardiovascular system. So if you increase blood volume, you increase venous return to the heart. If you increase venous blood return to the heart, then you are going to increase blood pressure. So, and that is done through certain hormones, mainly renin, which is going to be converted to angiotensin type 2, which is going to stimulate hormones such as aldosterone and vasopressin, but we'll be talking about that ad nauseum. Now, the next one is it is going to regulate osmolarity. Now, I'm blanking on the exact value that the book gives you, but just for simplicity's sake, we'll say it's 300. So what the renal system is going to do is it is going to maintain this number with very little variation in there. So it is going to control how concentrated your blood is to maintain this very strict value. I don't think it's exactly 300, but I think it's pretty close. Your book has the exact value. Maintains ion balance. If you have had a blood test done that tests for electrolytes, you will see that the reference range is very narrow. And if your renal system is working correctly, it will maintain a very tight regulation of the ion concentration in your body. So it maintains ion balance by controlling reabsorption, as they say, plus excretion. When you reabsorb something, you return it to the blood. When you excrete something, you remove it from the body. Now, when I say that the blood plasma is filtered by the kidneys, I mean all of it. Throughout the day, your blood plasma will be cycled through the kidneys. Well, the functional units of the kidneys, called the nephrons, it's going to be filtered through there multiple times a day, and I mean all of it. And the functional units of the kidney, the nephrons, they determine whether or not to excrete ions or send them back into the blood. Reason why it's called reabsorption is because it's absorbed the first time in the digestive system. When your food is digested, things like ions, they are absorbed in your blood for the first time. When it's returned from the nephron, it's reabsorbed, meaning, well, absorbed again. Adding on to that is maintaining blood pH. This is also a very tightly regulated process. So maintains blood pH. What it does is it does that by controlling excretion plus reabsorption of these two compounds that we talked about are found in the blood: bicarbonate and hydrogen ions. So it can control the concentration of these two in the blood in order to maintain a proper blood pH. Next is going to be removes waste. I'll just go ahead and add this all to the same page. Removes waste. So the body is a monument of repurposing and recycling. There's some things that cannot be repurposed or recycled. They're waste products, and they can become toxic in high concentrations. These are metabolic waste products. Examples of these are going to be things like creatinine, things like uric acid and urea, things like what we call xenobiotics, which we'll talk about the next one. Xenobiotics. Of course, it can only do so within limits. If you decide that you're going to be, I don't know, a bro and have 300 grams of protein a day, because that's what bodybuilding.com says you should do, then your kidneys cannot exactly handle that degree of urea produced as a byproduct. And in theory, you can get stones, kidney stones that are comprised of uric acid. Not that ever happened to me or anything. Just throwing it out there. All right, so let's talk a bit about xenobiotics. So xenobiotics have a foreign origin. Now, when you take a medication, there's going to be a clearance rate, which is why there's some compounds you can find in the blood. If you've ever had a drug test done for work, you probably would see that they have you do a urine test. And the reason for that is because when these xenobiotics, when they flow throughout the kidneys, the nephrons have the ability to keep these foreign compounds in the nephron, so it is excreted as urine. One example is that, and you can go online and research many, but penicillin. One of the main challenges when penicillin was first discovered was finding a way to keep the kidneys from excreting it too fast. They did find a solution. They combined it with something else, but I don't know off the top of my head. I'll look it up. It's pretty interesting. The origins of penicillin are pretty interesting. So xenobiotics means a foreign origin. And lastly, it is going to produce several hormones. So produces hormones. Okay, examples of hormones. One is going to be one called aldosterone. And aldosterone controls sodium reabsorption. So it's responsible for returning water or filtrate to the blood to increase blood volume and increase blood pressure. Another one is going to be called erythropoietin. And I need to look how to spell this because it is a tough one. Actually, I don't need to spell it. I'll just call it ETH, which I think is its abbreviation. And this increased red blood cell count. This is a hormone that is naturally secreted in higher quantities if you are located in a hypoxic environment over long periods of time. So let's say that you live in the mountains. Long term, your kidneys are going to secrete more erythropoietin, which will increase your red blood cell count. What that does is it increases the amount of hemoglobin available to bind to oxygen. So what it does is it makes your body more efficient at, well, not efficient, but it allows you to have more red blood cells to capture more of the oxygen that is available. If any of you remember the Lance Armstrong controversy, this is one of the drugs he abused, because if you were into sports, in theory, if you are an endurance athlete, and you could increase the amount of red blood cells available to bind to oxygen, then you can do endurance activities longer without switching to anaerobic respiration, so it can increase your endurance. All right, so this is done with the functions of the renal system. Now we're going to go ahead and talk about the anatomy. So we have here the anatomy of the kidney, one of my favorite things to go over. So I'm going to draw the kidney here, just an outline of it. Kind of looks like this. Let's see if I can get it on the first try. Hey, not bad. So the first thing that we're going to talk about is the outer layer of the kidney. It's a tough fibrous covering, and it is called the capsule. I'm going to call it like this. Capsule is like a protective layer. The capsule. What's interesting about the capsule is that it actually has the highest density of nociceptors of any organ outside of the lungs. So that's why when someone has kidney stones and the kidney becomes inflamed, why it causes so much pain because of the high density nociceptors on there. What's also interesting is that the right kidney sits slightly lower than the left one outside of the thoracic cage, which is why the kidneys, especially the right one, are covered in fat, so it can kind of act as a cushion. But in boxing and other sports, there's something called the kidney punch, and it's effective because, well, it really hurts. Now, the next part, which I'm going to shade here in blue, is going to be called the cortex. The cortex has the majority of the blood vessels, and the blood vessels are going to feed into the nephron, and that's found in the cortex. And the next part is going to be what's called the renal medulla, which I'll shade here in green. Medulla means middle, and this is where most of the filtrate is converted into urine in the medulla here. And then this area here is going to be the renal pelvis, where what's left in the renal pelvis is eventually going to become urine. So these are the different layers. The cortex has most of the blood vessels. The medulla is where most of the filtrate goes that's going to become urine. And then this here is going to be the pelvis. And the renal pelvis is more or less whatever's left in there is going to go into the ureter and become urine. Now, since urine contains ions and minerals, is if you consume too much of one mineral and don't drink enough water, it's possible for what we call stones to develop. And if these stones get too big and break off, they're going to try and pass through the ureter, and there really is not enough space. We can get caught here and cause an incredible amount of pain. All right, so now we're going to draw another kidney, and we're going to talk about the anatomy a bit more. I have brown selected, so I'll just go with that. Nothing more appealing than a brown kidney. Kind of looks like a kidney bean. All right, so we talked before about the cortex, and as we talked about, it has lots of blood vessels. Because of course the artery that feeds into the kidney is going to branch off. So I'm going to draw here the arteries of the cortex. Kind of going to go a bit faster here, but it kind of gives you the idea. It feeds into the functional units called the nephron. And now I'm going to draw what's called renal pyramids. What's in the renal pyramids, it's mainly where the collecting ducts of the nephrons are located. And some of the nephrons will also be located in the renal pyramids. And they kind of look like this. The number of pyramids you have is based on genetics. Some people have more, some people have less. Bottom line is that a healthy person has between 1 million nephrons and between, I think, like 600,000 and 1 million nephrons, which really doesn't matter because a healthy person, even at maximal use, only uses about 20% of their kidney function, which is why someone can donate a kidney and still live a very full life. Okay, so these are the renal pyramid, and they are connected, and it's hard for me to show this on a two-dimensional drawing, but there is something called a calyce or a calyx. And these are found right at the bottom of the tip where the renal pyramids terminate. So these here in purple are the calyces, and the calyces eventually are going to dump urine into the renal pelvis, as they call it. And there's two calyces here, major and minor, but I won't ask you to know the difference. And then nice yellow color, whatever ends up in the renal pelvis, going to go into the ureter as urine. Okay, and after this, we are now going to talk about nephrons. All right, everyone, so we're now at part 2 of our journey through the renal system. And now we're going to talk about the functional unit of the renal system, and that's the nephrons. And the nephrons, as I said, there's between 600,000 and 1 million of them in each kidney, depending on your personal physiology. This is determined on genetics, does not determined by any lifestyle factors. Of course, later in life, if you have renal failure, then it is very, very possible that you can reduce the number of nephrons to a point where it is at dangerous levels for you. So anyways, I'm going to draw here a renal pyramid. And the renal pyramid, as I talked about, contains most of the bottom half of the nephrons. And I'll show you what I mean by that. So this is a renal pyramid. And first, we need to talk about the two types of nephrons. The first one is called a cortical nephron. If you're thinking that it's called the cortical nephron because it starts in the cortex, then you would be very right. So this space here is going to be the cortex. And this space on the bottom here, deep where the pyramid is, this space is actually called the renal medulla. Medulla means middle in our favorite language, Latin. So the renal artery is going to go into the kidney. It's going to be the largest artery. It's going to branch off. You remember your anatomy. It's going to branch into a series of smaller arterioles. And each nephron is going to begin with an afferent arteriole. Then it is going to turn into a ball of capillaries that we call the glomerulus, like so. And then it's going to exit with an efferent arteriole. Each time the blood plasma passes through the glomerulus, it's going to lose 20% of its plasma to the nephron. Now, you might be thinking, well, why only 20%, not more? Well, if our blood is basically all solids, it's not going to flow anymore. But keep in mind is that our blood flows through the renal system dozens of times a day. So eventually all that 20% is going to get filtered. Now, the cortical nephron, well, all nephrons, are going to begin with what's called a Bowman's capsule. Going to look like this kind of. So what's going to happen is that filtrate, and we'll talk about the pressure factors that cause plasma to enter the Bowman's capsule. The filtrate is going to enter the Bowman's capsule, and it's going to go through a series of tubing. And the tubing is going to start with what is called the proximal tubule. Don't worry, we're going to go into this ad nauseum in a bit. Then we're going to have the nephron loop. Then it's going to turn into the distal tubule. And then the distal tubule is going to terminate into what is called the collecting duct. I know this is not the best nephron I've drawn, but I'm a bit rusty with it. And the collecting duct is actually going to go down further down the renal pyramid. I just drew it a little bit short. We'll pretend we cut it. Now, the other type of nephron is going to be called the juxta, which means next to, juxtamedullary nephron. Juxtamedullary means next to the middle. And I say that because the nephron is going to begin right above the renal pyramid. So you have the afferent arteriole, the glomerulus. We're going to have the efferent arteriole, and then we're going to have the beginnings of the nephron. Also going to have a Bowman's capsule. And this one is going to be a bit unique because in addition to starting lower in the cortex, it's going to have a deeper nephron loop. Yeah, as I said, this is not the best nephron to draw in the world, but just to illustrate a point. So the nephron loop is actually going to go deeper into the renal pyramid. And it does so because, as we'll talk about, is the renal medulla is very concentrated. And the nephron is going to be permeable to water and ions. So in case you're kind of gathering what's going on here, is that the concentrated medulla is going to draw out water from the nephron loop. But as we'll talk about, most of the filtrate is actually going to be reabsorbed back into the blood in the proximal tubule, about 70%. Now, the nephron is going to be surrounded with what's called peritubular capillaries. So from the efferent neuron, the capillaries are going to surround the nephron. And the reason why it does this is because the bloodstream is constantly reabsorbing things from the nephron. The way that nephron works is kind of like, it's the same idea as when you clean out your garage. Is if you think about it, it's actually easier to take everything out of your garage, put it in your driveway, and then put back the things that you want, and the rest of it you leave outside for the dumpster. Putting things back into your garage is analogous to putting it back into your bloodstream. Leaving it out into the driveway is analogous to keeping it in the nephron so it becomes urine. Of course, the analogy falls apart when you kind of figure out you'll really anger your homeowners association or neighbors by leaving a bunch of junk on the driveway. But as I said, this is only a hypothetical scenario. So about 80% of our nephrons are actually cortical nephrons. Juxtamedullary nephrons, the purpose behind them is they return more water to the blood. And that's the two types of nephrons. So now we're going to actually talk about the nephron, and I should have practiced this first. But anyways, we're going to start with the afferent arteriole. It's going to turn into the glomerulus, which is the ball of capillaries that I was mentioning earlier. Then we're going to have the efferent neuron. Now we're going to have the beginnings of the nephron. So we have what's called the Bowman's capsule, like so. And then we're going to have the first part of the nephron called the proximal convoluted tubule. It's called convoluted because, as you can probably imagine, it's very twisted. We're going to go like this, and like this. Then it's going to become something called the loop of Henle. Like so. Going to loop around. It's also called the nephron loop because, well, that's what it is. After the nephron loop, we're going to have the distal convoluted tubule, which, as we talked about, is distal, like so. nice and convoluted. And then we're going to terminate with the collecting duct. And once urine becomes the collecting duct, it's basic, or enters the collecting duct, it's basically going to become urine, even though there still is some room for reabsorption. So I'm going to shade in purple, I'm going to shade the pink, the proximal tubule, like so. And as I said, this is where most of the reabsorption occurs. And then we're going to have in orange, we're going to have the nephron loop, also known as the loop of Henle. I tend to interchange the two, so heads up on that. So this is the nephron loop. And then in green, we're going to have the distal convoluted tubule. And I just write distal tubule, but it can also go by DCT, and proximal tubule can go by PCT. When you go like this. And then finally, we're going to have the collecting duct, which we'll do in blue. Actually, yellow. Yellow is very appropriate at this time. Collecting duct. And the collecting duct is in yellow, and it's going to become urine. So these are the parts of the nephron, and as I said, the peritubular capillaries are going to be surrounding the nephron. I'm not going to draw super overlapping because that would be way too much for my artistic abilities. But it's going to basically follow the nephron around, and it is going to constantly be reabsorbing things that the bloodstream wants back. Because as I said before, at least I think I said that, is that in the nephron, everything that almost everything small that's dissolved into the water or carried in the filtrate is going to go into the nephron. All right, we're going to talk about some vocabulary here before we continue. And the first one is going to be called excretion. Now, excretion means to remove from the body. We talked about these terms a little bit earlier in the semester, but this is actually, it is no longer in the body. It is going to be excreted. It's going to be out. And things that are excreted are things that can no longer be recycled or used by the body, and it's in the body's best interest to get it out. Urine and excrement, I know excrement is excreted. I know that sounds shocking. We'll just call it solid waste to be a little bit more discreet about it. But excretion means removed from the body. Now, when I say that something is secreted, it means that it's going to go from the arterioles or the bloodstream to the nephron. That is right, is that even after filtration, the blood can still secrete things into the nephron. Now, after much deliberation, I have chosen not to include this in our Chapter 19, Chapter 20 lecture, other than this small snippet, because I'm trying to show the concept of reabsorption and excretion. And if we're going to talk about secretion, it's going to add complications to an already complicated topic. So I'm sure if you go on to more advanced physiology classes, that they will talk more about secretion in the renal tubules, but I have chosen not to, other than this small snippet. And the last one is going to be reabsorption. And reabsorption is going to go from the nephron tubules to the blood. And this is the main thing that's going to happen during the process of nephron filtration. Is things that the body needs back are going to be reabsorbed into the blood. So one thing that's interesting is lots of things that we take in our daily lives, for example, like multivitamins, most of the time they're dumped into the nephrons, and and the nephrons will only reabsorb a tiny bit of it because that's all that you need, and the rest is going to become urine. So depending on how many vitamins you take, it could be very expensive urine. The one exception to that is going to be fat-soluble vitamins like vitamin D and vitamin A, because they're not actually going to be water soluble. All right, so that is all for the nephron parts. And next we're going to be talking more about the process of filtration. All right, everyone, welcome aboard. As I begin this Zoom meeting, it becomes apparent I drastically need a haircut and probably could do to maybe trim the beard again. I find with me is that I have a very narrow range between kind of a maybe athletic haggard look and homeless. That line is very thin, and I think I'm starting to venture more into the homeless side of things. But anyways, the real reason why you came here is to learn about the glomerulus and the glomerular filtration rate. So let's go ahead and draw here. Go ahead and draw the Bowman's capsule. So this is going to be a rather large Bowman's capsule, and the Bowman's capsule is a closed environment, actually, and we'll talk about what that means in a bit. But this is the glomerulus. And what I'm going to do is I'm going to draw just one capillary, because even though you know that the glomerulus is a ball of capillaries, I'm just going to draw one, like so. And this is going to be, I guess, what you can call a side view. So we are going to have endothelium here. We're going to have some basement membrane, so highlighted black. And we are going to have these foot-like processes. And if you are to take your fingers and loosely interlock them, like this, or do you know what? Hold on. Pretend that this is the capillary. Pretend that my fingers here are what we call the podocytes. And if you look here, if you look at my fingers, if you were to pretend that this soda can was filled with holes, you would see that liquid can leak out of this can. Now, with filtration, that's what we want, but these fingers being overlapped would prevent anything large from getting out. Like, let's say there was some, I don't know, pebbles in this can. The liquid would get out, but not anything big. So that same analogy works with something called the podocytes, and they surround each capillary in the glomerulus. So what these are is it's basically a wrapping. So it's a wrapping that looks like this. So you see here that these podocytes, foot-like processes, they are going to surround each capillary, and it's going to create a concept called microfiltration. Micro means small, filtration means to, well, I guess you can say to rid of solids. We'll go ahead and say that. So it's microfiltration. Why can I not spell filtration? Microfiltration. Okay, so what are the barriers that prevent large things from passing through the capillaries? Now keep in mind that we only have 20% of plasma entering the capsule. So how does this microfiltration work? Well, so first of all, these are our special capillaries that we call fenestrated capillaries. A fenestration is a window. Now, these are capillaries that are designed to be very leaky. So if I'm going to draw one again, I don't think I drew fenestrations in this one, but it's going to look like this. So these capillaries are going to be very leaky. And that, of course, is by design because we're trying to get plasma from the glomerulus into the Bowman's capsule and ultimately into the nephron. Now, the next filtering barrier is what we call basement membrane. Basement membrane is attached to the capillary itself. That also is a minor barrier. And last of all, we have what's arguably the most important part. We have the podocytes. So what this does is it is going to prevents proteins and cells from diffusing into the nephron. Please keep in mind the nephron is not designed to handle large proteins. So the combination of fenestrated capillaries, basement, why did I do basement capillary? What's wrong with me? Basement membrane and podocytes, those are three components that create microfiltration. Yes, the two types of capillaries, fenestrated and basement capillaries. Basement capillaries obviously are in the basement of the body. Yeah, that actually could work, sure. So what are the kinds of molecules able to pass through? Well, I mean, I think it would be kind of redundant to say small. But first, let's talk about the things that can't. As we talked about proteins and cells. So what can be filtered? So molecules that can be filtered. Okay, the first is going to be ions. Small compounds such, or not compound, but small things like ions are able to pass through. Glucose and amino acids. These are going to be two macromolecules that can be filtered. Okay, then we are going to have waste products such as urea, creatinine, uric acid. There's actually a test with creatinine called the, I believe it's called the creatinine filtration rate test. So what it is creatinine is a waste product that is usually not reabsorbed well into the blood. So if creatinine in the blood is high, that means it isn't being filtered properly by the nephrons. So that's a function of how well the kidneys are working. Okay, so, and of course, the big one is going to be, water. Give me 1 second here. Phone calls really are not friendly to Zooming. And of course, we're going to have water. So those are the things that are going to be filtered into the nephron. Okay, so next up, we are going to have, let me get back to the outline here. So next up, we are going to have something called glomerular filtration rate. Let's go ahead and talk about this. So glomerular filtration rate, move this up a bit, or GFR, filtration rate, is generally recognized as far as liters per day. And as we talked about before, it's about, if you're an average adult male, about 180 liters per day. But of course, it's going to differ depending on your body mass. Now GFR is driven by a couple of forces in the body. So I'm going to draw here again a Bowman's capsule. Let's get a little bit fancy with it this time. No, that's getting fancy with it was a really bad idea. All right, so this is another Bowman's capsule. And this is going to be a capillary. Remember, it's fenestrated. So this is going to be our capillary. As I said, I'm only drawing one capillary, but just remember that this is a ball of capillaries. All right, sorry about that. I had to turn my phone on Do Not Disturb because telemarketers do enjoy calling on Sunday nights. All right, so right on, we are back. So we're going to have a single capillary, as I said, actually a ball of capillaries. I'm not going to bother drawing anything else in here. Okay, so the driving force of GFR is going to be what we call hydrostatic pressure. And we already did talk about hydrostatic pressure. So I'm going to go ahead and draw GFR here. So we have hydrostatic pressure. Now, when we talked about the cardiovascular system, there was a big difference. And that difference was that those blood vessels were not fenestrated. So because of that, liquid was not pushed out. And that is going to be something significant because these capillaries are not designed to hold pressure. What's going to happen here is that whenever these capillaries are subject to hydrostatic pressure, what's going to happen is that water and filtrates are going to be pushed out of the capillaries and into the Bowman's capsule. So this is going to be at a pressure. Actually, just for clarity's sake, let me write this in blue. So this is going to be at a pressure of about 55 millimeters of mercury. So it is about 55 millimeters of mercury of pressure is going out into the Bowman's capsule. Now, this is going to be opposed by certain pressures. And the first thing is something that we have not talked about. It is called osmotic or colloid pressure. Now, thinking about osmosis, we talked about in osmotic gradients. And of course, water is going to go to the more concentrated environment. And that amount is determinant on the concentration of non-diffusible solutes. So when there are large things in the blood, such as proteins and cells, what's going to happen is that during diastole, so during systole, that's when hydrostatic pressure is the driving force of filtrate movement into the capsule. During diastole, some of that filtrate is going to be pulled back in. So osmotic pressure is going to go from the capsule, going to be sucked back into the capillaries. So I'll just put down glomerulus. And just so we're staying tidy, it's going to be from capillaries. Actually, let me stay consistent here. Glomerulus to capsule. Now, what is the amount of colloid or osmotic pressure? About 30 millimeters of mercury. But there is another variable too. We call this fluid pressure. And this one is also going to be from the capsule to the glomerulus. So this is opposing hydrostatic pressure. And what it's doing is it is encouraging filtrate movement back into the glomerular capillaries. Now, why is this? Well, the Bowman's capsule is actually a closed system. And because it's closed, whenever filtrate is pushed into the Bowman's capsule, some of it is going to be forced back in because we know that pressure is forced against the walls of the container, and if the container has nowhere to go, if the filtrate has nowhere to go into the container, then some of it is going to go back in. So if I'm going to draw an arrow, it's going to look like this. So hydrostatic pressure is going to push out. This is closed. And then what's going to happen is it's going to bounce right back in. Now, of course, bounce is not a very scientific term, but it's basically going to be resisted by the closed environment of the Bowman's capsule, and it's going to be pushed back into the glomerular capillaries. So this pressure is going to be the equivalent of about 15 millimeters of mercury. So we're seeing here that we have two forces. So GFR, that's G. GFR is the determinant to 55, which is hydrostatic pressure, minus 30, which is going to be osmotic pressure, minus 15, which is fluid pressure, equals 10 millimeters of mercury. And this is going to be net filtration pressure. Okay, so that is going to be the glomerular filtration rate. Now, are there ways to adjust glomerular filtration rate? Under certain circumstances, can we actually increase or decrease GFR? Well, sure we can. Because recall that we have arterioles, and arterioles are comprised of smooth muscle. So this is the glomerular capillaries. And then this is going to be the efferent arteriole. I will talk about this later, but there's actually receptors here. Receptors here called baroreceptors. And we haven't talked about these much, but you may remember them from anatomy. So what baroreceptors are is they detect physical pressure. So they detect physical pressure. And the response is going to be vasoconstriction. So the higher the pressure, then the greater vasoconstriction is. So the idea is that you don't want too much pressure going into the Bowman's capsule, because the Bowman's capsule can be damaged if GFR is too high. Low blood pressure is dangerous in the short term. High blood pressure is dangerous over the long term. Okay, so let's say that you want to, let's just say we are going to do an experiment. Let's say that we are going to increase, actually we'll say afferent arterial. Let's talk about some things here. So let's say that we want to increase vasoconstriction. Well, recall here that one of the resistance factors for blood flow is going to be radius. So what's going to happen if you decrease the radius? Well, if you decrease the radius, you're going to increase resistance. Because recall that the larger the radius, the greater the flow rate. So with this, you're pretty much building in a restriction point. This is going to reduce GFR. Now, the same thing is going to be true of the inverse. If you decrease vasoconstriction, vasodilation, you're going to decrease resistance and you're going to increase GFR. So this is going to be vasoconstriction. If you reduce vasoconstriction, which is going to end up being dilation, you are going to decrease resistance and increase GFR. So actually this is kind of confusing. So what I'm going to do is I'm going to write down, yeah, let me stop being lazy. So we are going to do is if we increase vasodilation, and just to help with understanding, I'm going to build in some arbitrary numbers. I'll say that we're going to start off at, so let's say baseline is going to be 10 millimeters. And let's just go ahead and say that if we vasoconstrict, let's say it's going to be 7 millimeters. And if we vasodilate, just as I said, arbitrary numbers, we'll say that's going to be 12 millimeters. What that's going to do is it's going to decrease resistance, which is going to increase GFR. And this is called myogenic autoregulation. Myo as in muscles, auto as in self-regulate, so self-control. The muscles control themselves. Okay, so now we're going to talk about the efferent arterial. And I did make a little bit of I put a little bit more information here. So this here is both related to the efferent arterial in both green and orange. So if we look here, the efferent arterial controls blood exiting the glomerular capillaries. Now, we already talked about what's going to happen with the afferent arterial. But what about the efferent arterial? Well, here we have some more arbitrary values with a baseline. Now, let's say we increase vasodilation. We are going to decrease resistance of blood leaving the glomerulus, which means that it can leave easier. However, that is going to decrease GFR. And the reason why is that recall that pressure is force against the walls of the container. And if you make it harder for something to leave, well, then it's going to stay in the glomerular capillaries longer. If blood stays in the glomerular capillaries longer, then it's going to allow filtration to occur over a greater time period. So basically, by keeping things vasodilated, you are going to make it easier for blood to leave the glomerulus, and that's actually going to decrease GFR because blood will spend less time in the glomerulus as it will move through faster. And the opposite is going to be true if you vasoconstrict the efferent arterial, because you are going to, okay, this arrow is definitely not right. because what you are going to do is you are going to increase resistance of blood leaving the glomerular capillaries. That means they'll be in there longer and filtration rate will go up. And that's because blood will stay longer in the glomerular capillaries for filtration to happen. So basically, it just depends on how much time blood is going to stay in the glomerulus. With the efferent arterial, if it's open more, it's going to decrease resistance of blood leaving the efferent arterioles, and it is going to decrease GFR because it'll be easier for blood to leave. With the efferent arterial, if you increase vasoconstriction, you're going to increase resistance of blood leaving the glomerulus, but you are going to increase GFR. Those are the basics of glomerular filtration rate and the effects of afferent and efferent dilation or constriction. It's very important that you understand these for the upcoming exam. All right, everyone, well, we are back talking about the nephron. Now, when I draw the nephron here, keep in mind it does not really look like this. It's just for ease of teaching. Really, it's highly convoluted. So this is how it's going to look in reality. So I'm just going to draw a straight line. It's going to be real convoluted like this. It's going to kind of go behind, loop of Henle. Distal tubule is going to go back around, and then you are going to have the collecting duct here. So it's actually highly convoluted, but for ease of learning, we're going to draw it, well, easily. So we're going to start with the Bowman's capsule, like so. And it's going to look like this. And recall that we have the glomerular capillaries, like so, efferent arterial. And we're going to start by drawing the PCT, also known as the proximal convoluted tubule. Actually going to look rather like this. And then we're going to have the loop of Henle. So if we look here, it's going to go all the way down like so, loop around. It's going to start off thicker on top, then it's going to narrow a bit. And then once again get thicker. We are going to have the DCT, like so. Let's get it nice and convoluted here because it is the distal convoluted tubule. Like so. Great. So this is how it is going to look. And as I said, this here is the proximal tubule. And this here is loop of Henle, the distal tubule. And, oh gosh, it looks like I made a mistake here. But yeah, you get the idea. Distal tubule and collecting duct. We're going to talk first about this part here. And this part is going to be the proximal convoluted tubule. So I'm going to go ahead here and I'm going to draw it like this. So we'll go ahead and draw it in black here, just for authenticity's sake. So this is going to be the PCT. I'm going to draw it nice and big. And so PCT, proximal convoluted tubule. Now this is actually comprised of cells that we call simple cuboidal epithelium. So it's not the prettiest diagram in the world, but these cells are going to look like this. So we're actually going to have three environments here. We are going to have the filtrate, we are going to have the intracellular environment, and then we are going to have the blood. We'll just consider the blood and the extracellular environment sort of one and the same for ease of teaching. Now the proximal convoluted tubule is actually the site that's most active for reabsorption. So let's talk about some things that are reabsorbed. Well, about 70% of ions are going to be reabsorbed, meaning they're going to go from the filtrate back to the blood. About 70% of water is going to be reabsorbed because, as we talk about, water follows sodium. Sodium is an ion. Now, what should be is 100% of sodium, not sodium, of amino acids and glucose. If 100% of glucose is not reabsorbed, that means there's too much in the filtrate. Why would there be too much in the filtrate? Well, because there's not enough insulin to tell the cells to take in glucose from the blood. Therefore, the glucose stays in the blood, it gets dumped into the nephron, and if there's too much, it can't be reabsorbed. And the PCT is the only part of the nephron that can reabsorb glucose because it has GLUT channels. We're also going to have about 50% of waste products, such as of urea. And urea staying in the filtrate is actually going to be a valuable thing, as we'll talk about in a bit. So we are going to have about 50% of urea. So, as I said, the PCT is actually going to control 70% of water, ions. It should reabsorb all amino acids, all of the glucose, because the body's spent a long time, lots of effort and energy trying to reabsorb that. As far as waste products go, most of them are going to stay in the nephron, but some of it's going to be reabsorbed. Usually here you are going to have 100% of xenobiotics going to remain into the nephron. Also, excess vitamins and minerals are going to stay in the nephron as well. Okay, so how exactly does this process work? Well, it actually has to do with efficiency, mainly with symporters. So let me get my diagram ready. This is 19.8, and I want to get my diagram ready to make sure I don't make any mistakes here. One thing about teaching, and you'll see this in my videos on occasion when it's like, it just ends and then I integrate a new one. I could nail every part of the lesson, and if I just get confused on one concept, the entire video is ruined. Usually in class, I can just say, oh yeah, sorry, but when you're doing a video, it's permanent record, as they say. So I try and be a little bit more organized. So this is a cell here. And what I'm going to draw here in orange is going to be a sodium anion symporter. So I'll put this in orange. Is going to be a sodium anion symporter. So it's going to be an Na plus Na plus anion symporter. And what this is going to do is it is going to drive an electrochemical gradient. So what it is going to do is that this is going to be the lumen, and this is going to be out here, it is going to be the blood. So it's going to look like, I'll just do one red line. Okay, so what is going to happen is that from the filtrate, you are going to have sodium being absorbed back into the cell. So it is going to go from the lumen into the intracellular environment. And then we're also going to have anion movement. Excuse me. Now, what this is going to do, because recall that water follows sodium, what this is going to do as well, so I'm going to draw here another cuboidal cell with a little bit of space, just so I can, actually that's going to take up too much room. So we're going to have a very small, simple cuboidal cell this time. So what this is going to do is, as I said, water follows sodium. Therefore, water is going to enter through aquaporins. So this is going to be an aquaporin. And water is also going to move through paracellular transport. And that is triggered by sodium movement. Water follows sodium. Now, what we also have is other channels that are going to transport things like potassium. So I'll do K plus. So this is going to be a K plus channel. We're also going to have things like calcium is also going to be reabsorbed. As I said, these are not things that you want dumped into the urine unless you have way too much of one solute. So these are all things that are going to go into the cell. And what's going to happen here is that we have things such as, and the book doesn't go into detail on this, so I won't either. But you have things like the Na plus K plus pump, which is going to return sodium outside back into the blood, which is what you want. Going to move potassium back into the cell. And then what that is going to do is it's going to continue to drive water movement into the blood. Now, one example of a symporter here is going to be what we call the SGLT symporter. So I'm going to draw another cell here. And this is an example of a co-transporter. And this shows you how efficient transport is in the nephron. So what's going to happen here is that we are going to have a symporter called SGLT. That's right here, SGLT. It is going to actively transport sodium and glucose. And glucose, as we talked about, has a negative charge. So what's going to happen here is that in the lumen, we are going to have sodium. Here, I'll do it in purple this time. So sodium is going to be in pink. Go ahead and say that glucose is going to be in green. I don't know why I associate glucose with green, probably because it starts with a G. So what's going to happen here is that sodium is going to be actively transported into the cell. Now, one thing to keep in mind is that Na plus is going to be high in the lumen and glucose is going to be low. Of course, this process can be altered a bit if there is way too much glucose in the lumen, but it's not going to impact things that much because sodium is the driving force. So sodium is going to be transported actively, and the glucose is going to move through passively. By the way, the reason why they call diabetes mellitus, the reason why it's called diabetes is because diabetes means excess water loss. So what happens is that glucose is also highly osmotic. If there's too much glucose in the lumen of the nephron, what it's going to do is it's going to act almost like a colloid pressure effect, and it's going to keep water from being reabsorbed into the blood. So basically, if somebody has excessive glucose in the blood, or sorry, in the urine, that's going to be paired with excess water because of how hyperosmotic glucose is, which is why excessive urination is a marker of diabetes mellitus. Mellitus means sweet, so it literally means sweet pea. And in the old days, before they had medical tests, how did they know that there was sugar, um, excessive glucose in the urine? Well, they tasted it. More like they had their interns taste it. And that's how you knew. Just imagine that being a part of nursing school or medical school. I'm pretty sure this class wouldn't be quite as popular. All right, so sodium is going to move through actively, and glucose is going to move passively. And this is called secondary reactive transport because sodium is being moved through primary transport and glucose is being moved through secondary transport. Now, inside the lumen, things are going to change. Comparatively, glucose is going to be found in high concentrations. Now, why is that? Well, because cells are constantly getting glucose via cellular respiration. And sodium is going to be in a low concentration because, as we know, sodium-potassium pumps are constantly getting it out of the cell. So we have a high concentration of glucose and a low concentration of sodium in the cell, in the intracellular environment. We'll go ahead and put a box around this so this is going to be intracellular. And this here is going to be in the lumen. So now we are going to have here, we are going to have the extracellular. I'll just put in here extracellular. And extracellular is basically just a buffer between the blood and the cell. I think I spelled extracellular. Oh my gosh, that is not how you spell cellular. What's wrong with you, teacher? I swear I graduated grade school. So we have extracellular. So what's going to happen here is that, so I'm going to erase this because you get the idea, is sodium is now going to leave via the Na plus K plus pump, which I'll put here in red. So we are going to have sodium is going to move out of the cell, and potassium is going to move in. And we're actually going to have a carrier channel called a GLUT transporter. And it's going to look like this. It's called GLT. I'll just mark it with GLT here. And this is going to move glucose from the intracellular environment to the extracellular environment. So let's talk here again how the SGLT symporter works. This is just one example of a transporter in the nephron. So the SGLT symporter is going to move sodium, which is in high concentrations. It's going to move that into the cell actively, because recall that it wants to move as much sodium as possible. It doesn't want to reach equilibrium because that means only half the sodium would be reabsorbed, which would drastically alter water reabsorption. This is going to move along sodium, glucose, because as we see, since glucose is in relatively low concentrations compared to the cell, then what that means is that glucose would not diffuse in. So once again, compared to the inside of the cell, sodium is high, and compared to the inside of the cell, glucose is low. Now once you have, and this is an example of secondary reactive transport, because the sodium is moved in actively, and the glucose is going to follow down that gradient, because a positively charged ion can move a negatively charged molecule. So what's going to happen is that in the cell, compared to the lumen, glucose is going to be high and sodium is going to be low. It doesn't matter. The sodium is going to be moved out via the sodium-potassium pump, which is exactly why sodium is low in this case. And glucose is going to be moved out via the GLUT channel, or GLUT transporter. And in the end, that's how you get both sodium and glucose back into the blood. Okay, so next we are going to talk about the loop of Henle. And this is actually one of my favorite things because it uses something called countercurrent multiplication. So we're going to start by drawing the loop of Henle. It's going to look like this. It's going to be a very big loop of Henle, like so. Let's make it bigger. Okay, now there's two aspects of it. One aspect is called the descending loop, which is the one that is most proximal to the PCT. And then we are going to have we're going to have to do this small, ascending loop. Now what's interesting is that the descending loop is permeable to H2O, but it's going to be impermeable to ions. So basically everything else, but we'll just say ions. So what this means is that the only things that you can find here are going to be aquaporins, which I'll just put here in blue. Okay, now keep in mind also this is a two-dimensional image, so I'm going to draw in the center here the conditions of the renal medulla. Now the ascending loop is a bit unique because H2O is going to be impermeable. Told you it was going to be small. And ions are going to be permeable. So it's going to be the complete opposite. In fact, in here, we actually have a familiar symporter called the Na plus, or sorry, let's make it easier, NKCC symporter, which, as you remember, sodium, potassium, and in a roundabout way, 2 Cl2 minuses are going to end up from the lumen into the extracellular environment, more or less. So this is going to be the main transporter in the ascending loop. We're also going to have a urea transporter, which is very important because urea is a large molecule that is highly osmotic. And basically what the goal is that in the renal medulla, the goal is that we want to make the lumen, not lumen, we want to make the environment extremely hyperosmotic. That is the goal. And to do so, you want to make it concentrated with ions and urea. Now, why would we want to make it hyperosmotic? Well, it's a bit interesting because the ascending loop's job is to transport out ions and urea, which is going to make this environment hyperosmotic. What that's going to do is it is going to draw water from the descending loop into the renal medulla, which will eventually be absorbed into the peritubular capillaries. So I'll draw here in red, just like this. Okay, now this is just a simple diagram to show also that some of it's going to be reabsorbed into the capillaries as well. But the idea is that you want the ions to be pumped out, urea to be pumped out into the renal medulla, and then you are going to have water as a side effect, not side effect, but as an intended effect, is going to be drawn out from the lumen into the extracellular environment. This is a very simplified diagram because, of course, these are all going to get pumped back into the blood. So in the loop of Henle, we're going to have about 25% of water reabsorbed and 25% of ions. So the ion movement here is going to trigger the water reabsorption here. As I said, I'm really simplifying this because we could probably spend an entire semester on nephrology. I think it's fascinating, but yeah, we're kind of forced to gloss over some things. All right, so what is going to happen here is that on the ascending loop, we're focusing on reabsorbing ions, and in the descending loop, we are focusing on reabsorbing water. We call this process counter because the two areas of flow go against each other. Current, because water is moving. Multiplication, because what is going on in the ascending loop is multiplying the amount of water reabsorbed. And this is just one example of countercurrent multiplication. In the nephron loop, 25% of water and ions are going to be reabsorbed. That is a very large amount because if you consider 25% of 180, now I'm not a math magician or anything, but that seems to me to be at least 40 liters of filtrate that needs to be reabsorbed in a 24-hour period. Obviously, that's huge. So there's actually something called diuretic, and recall that I said that diuresis is to urinate. So let's say that somebody has a problem, let's say a cardiovascular problem, and because of that they're prone to pulmonary edema. What you can do is you can take diuretic. What this would do is it would introduce an antagonist. What it would do is it would antagonize the NKCC symporter, and what that would do is that would prevent the ions from being moved out of the lumen. If you antagonize some of these channels, it's going to increase water and ions staying into the nephron, meaning it's going to increase water leaving the body through excretion. Diuretics are also unfortunately abused by athletes as well, especially those that are trying to cut weight, because of course we're made up a lot of water weight. And if you're trying to make weight for an event, then what's going to happen is that you can lose weight through rapid water excretion, since we're 70% water. So somebody takes a diuretic, which keep in mind these are banned in competitions, then they can lose a lot of water in a short period of time, and they can lose body mass for their weigh-in. This process is not good for the body. It's not kind, and people can go into a form of they can get very sick if they lose too much water too fast. So if you're looking forward to a boxing match or a UFC match, and the day before the fight, the competitor falls down with symptoms of the flu, that's usually because they tried to shed water too fast. And if you antagonize the NKCC channel, you are going to reduce the amount of water reabsorbed as well, which is going to result in this staying into the nephron loop. All right, so now we're going to be talking about the distal tubule. And the distal tubule is very interesting, and I will show you why in a moment. So by the time we get to the distal tubule, or the DCT, distal convoluted tubule, I guess you can say its unique attribute is the fact that it is variable reabsorption. And you probably say, well, why is it variable? And the answer is because other parts of the body, which we'll talk about for chapter 20, can communicate with it. And this is because this is the only part of the tubule that has two types of receptors. One is called aldosterone. It has a receptor for aldosterone. And it also has a receptor for something else called vasopressin. So by the time we get to the DCT, if you're doing your math correctly, it's always a challenge for me, we have about 5% of solutes. Well, actually, I don't like that terminology. Ions plus H2O left. Now, 5% is a large amount. Because as I said, if we're basing it off a guideline of 180, 5%, if my math is correct, is 9 liters. So we have variability of 9 liters that is controlled by aldosterone and vasopressin. So what aldosterone does, aldosterone controls Na plus sodium reabsorption. So basically, the greater the aldosterone, and this is going to be really important for chapter 20, the greater the aldosterone, the greater the reabsorption into blood. Now, guess what? With vasopressin, it's going to go hand in hand. Aldosterone and vasopressin, as you'll see in the case study, they really work best together. So vasopressin has to do with H2O reabsorption. And what this does is the greater the vasopressin, then the greater blood H2O reabsorption. Now recall that water follows sodium, which is why it's much more effective if you pair the two together. Now, the goal between these two hormones, so the goal is going to be increased blood volume. And we'll talk about that in chapter 20. But anyways, one of the main transporters here is called the Na plus Cl minus symporter. So it is going to move out sodium and chloride. Very similar manner as what we talked about with in the PCT, is you can have one positively charged ion, one negatively charged ion, which in this case it would need to be two sodiums because chlorine has a -2 charge. It's going to drive ion reabsorption through secondary active transport. There's also a class of diuretic called a thiazide diuretic. And this is from what I understand, more potassium sparing than loop diuretics. And I didn't tell you the name of them before, but they're called loop diuretics. These are not quite as potent because it only affects this one channel, the Na plus CO minus channel. What it does is it acts as a antagonist, which means that it prevents the reabsorption of these ions. Okay, so now we're going to talk about the collecting duct. And I gotta say that the collecting duct, if I'm being 100% accurate, there still can be some things reabsorbed through the collecting duct. But for the intended purposes of this course, we're going to say that it's 0. So what the collecting duct is it is a long tube that is going to drive the filtrate to become urine. So basically the remaining filtrate is going to be urine. And what this is going to do is all the collecting ducts for the nephron, they're going to collect into what is called the renal. It's going to go through the renal papilla, and then it's going to go to the renal pelvis, and then it is going to go to uh, the bladder for excretion. Now, what's interesting is some people ask, well, why is it that drinking seawater will actually dehydrate you more? And that has to go with osmolarity. So basically, our kidneys do not have the ability, from what I understand, seawater is so concentrated that by the time it gets into the nephrons, it's so osmotic that it's actually going to pull water into the nephron because it is so much more osmotic than our body can deal with. So basically, you are going to lose more water by drinking seawater. From what I've heard in TV shows and stuff, if you need water and you're stuck at sea, you have to suck it out of a fish, which I really hope I never have to test out. All right, so we've talked about the parts of the nephron, and now we are going to move on to bigger and better. Well, hello there, everyone. You are especially welcome to our talk on transport maximum of solutes in the nephron. So what we're trying to figure out here, and I'll just title this here, transport maximum or maximum wow, that looks ugly. There we go, transport maximum of substrates in nephron. Yikes. There we go. So if we've learned one thing about the nephron so far, is that all substrates that enter it are going to be transported. And they're going to be transported using transporters. And we know that looking way back to chapter 5 or chapter 6, we know that all transporters have a saturation point. And the saturation point is the maximum amount of the substrate that can be transported per given value of time. And we'll just say per minute. So I'm going to give you an example. I'm going to give you an example of glucose. And here's what's interesting about glucose. Well, most substrates in general is I'm going to show you something here that's called the filtration rate. Now, when I say filtration rate, what I mean is how much of a substrate, how much of it can actually leave the plasma and enter the nephron as filtrate. Well, let's go ahead and find out here. So I'm going to say here that the x-axis, I'm going to say that it's going to be plasma glucose and I'll just say that's going to be milligram per minute. And I'll give it values like, I don't know, 100, 300, 500, whatever. And we're going to say that on the y-axis, it's going to be filtration rates. Filtration rates. And I'll give it an arbitrary number. I'll just put in milliliter per minute. And I'll say it's, I don't know, 5, 10,
completely made up numbers. Don't read too much into these, please. And so on and so forth. So what's interesting here is it doesn't matter how much glucose, oh, and by the way, glucose is going to be our example substrate. It doesn't matter how much glucose is actually in the blood, because it doesn't matter how much is in there, you are going to be able to filter as much of it as is in the blood. What this means here is that there is no saturation point here. So no saturation points. So what this means is I can even put in 1,000 milligrams of glucose into the blood. It doesn't matter, because it will all be able to be filtered into the nephron. I could add in 2,000 milligrams of glucose, and guess what? When that 2,000 milligrams of glucose enters the glomerulus, it's going to be filtered into the nephron, and then it's going to become part of the filtrate. So there's absolutely no maximum of glucose that can be filtered into the nephron. Now, okay, that's all fine and good. So how does that relate to our transport maximum? So let's go back here to transport maximum. And transport maximum is based on quite a few things, but to keep it simple, we're just going to focus it on concentration of plasma and number of transporters. Now I'm going to draw here another graph. This is going to be the transport maximum of glucose. And this is going to be very similar to figure 19.9 in your book. And we'll do the y-axis as the transport rate. We'll go ahead and say that it's going to be milligram per minute. And I'll just loosely use the values that are in your book here, 8, 6, 4, 2, and 0. Then on the x-axis, we're going to do plasma concentration. And we'll go ahead and say there's also milligrams per milliliters. And we'll do something very similar here. Made up values, 2, 4, 6, 8, 10. Now, I'm going to use an example here. So I'm going to draw you an example nephron. And what I'm going to do is I'm going to draw some glucose transporters. And keep in mind that real glucose transporters are usually coupled with sodium. But just to keep it simple, I'm going to draw here 2 glucose transporters. Let's put here in green, I'll just call them glucose transporters, abbreviated GOU. And we'll just say that each of these can move 2 milligrams per minute. So since we have 2, then they can move a grand total of 4 milligrams per minute. Great. Now, if I decide that, or if 2 milligrams of glucose enters the nephron per minute, that's not a problem. Because recall that our transporters can actually move 2 milligrams per minute for a grand total of 4 milligrams per minute. So if we have that entered here, 2 milligrams of glucose in that 1 minute, they can each be transported just fine. And if our orange line is going to signify transport rate, if I'm going to enter 2 milligrams of glucose, then guess what? 2 milligrams can easily be transported in that minute. Okay, now what about if I enter a third one here? What if I now put 3 milligrams of glucose in the nephron per minute? Well, not a problem, because recall our transport maximum is 4 milligrams per minute. That third one can be moved just fine. So if I decide to put 3 here, I didn't put 3, so I'll just put 3 and I'll circle it here. I can actually put 3 milligrams of glucose in our plasma. Not a problem, because 3 will be able to be transported easily. So now I'm going to get a bit wild and crazy. I'm going to add a fourth one here. And check it out. That fourth one can also be transported, because recall that our transport max is 4 milligrams per minute. I've now put in 4 milligrams of glucose into the nephron for that 1 minute. So the fourth one, all right, we also can transport that. But now I'm going to get a bit greedy. I'm now going to put in a 5th milligram of glucose in that nephron in that 1 minute. And what's that going to do to our transport rates? It's going to level off, because recall that we only have enough glucose transporters to move 4 milligrams of glucose per minute. By the 5th one, it cannot be transported. And instead, it's going to continue untransported into the rest of the nephron. So what's its fate going to be? Well, there's only one place in the nephron where glucose transporters are located, and that's the proximal convoluted tubule. If it is not transported in the proximal convoluted tubule, it's not going to be transported. It's going to be excreted. And I'll talk about the significance of that later. So what's going to happen is, it doesn't matter how much more glucose enters the nephron. Maybe we're going to do 6 milligrams into the nephron per minute, maybe 8, maybe 10. It doesn't matter, because our transport rate is a maximum of 4 milligrams per minute. So it doesn't matter how many milligrams of glucose enter the proximal convoluted tubule. Only 4 can be transported, meaning that any more that I add is just going to remain untransported and is going to enter the rest of the nephron, where it cannot be transported and will eventually be excreted. So transport maximum is important, because anything that is not transported continues on into the rest of the nephron. And if that substrate is glucose, then it is not going to be transported, and it's going to continue on to be excreted. So that brings us to another point, and this is going to be excretion rates. So this graph's going to look similar. So on the y-axis, we're going to, well, let me label the graph first. Always a good habit. So I'm going to put here on the y-axis, I'm going to put down, give me 1 second here. I'm going to put down excretion rate, and I'll give it milligrams per minute. And I'll put here on the x-axis plasma concentration. And I'll title this milligrams per 100 milliliters. Give it the value similar of 100, 300, and 500. So what we're trying to see here is, how many milligrams of glucose can I put into the filtrate before it can no longer be transported? and it's going to look like this. So what this means here is very similar to what I showed you on the transport saturation graph a couple of minutes ago. Is you can add here 100 milligrams of glucose into the blood. As we know, there is no saturation point for filtration, so all 100 milligrams of the blood glucose is going to enter the nephron. And you know what? There's enough transporters in the nephron to transport all 100 milligrams of this glucose back into the blood. Great. Now, the issue comes when we get over 300 milligrams of glucose. So if there's 300 milligrams of glucose in the blood, that means 300 milligrams is going to be filtered into the nephron. If 300 milligrams of glucose enters the nephron, then there's just enough transporters to bring it all back, to transport it all back into the blood. But at this point here, we have reached our transport maximum. And we know that because any more milligrams of glucose that we add to the blood is going to enter the nephron, and it's not going to be transported out. There's going to be too much glucose into the proximal tubule, not enough transporters, and it's going to keep on moving right through until it is excreted. And the higher the concentration past this 300 milligrams, then the more of it is going to be excreted out of the body. All right, so this is our take-home message here, is that for each substrate, there is going to be a saturation point, meaning that if the substrate enters the nephron, only so much of it can be transported out of the nephron and back into the blood. If the substrate concentration is too high and there's not enough transporters, then the remaining substrate is going to continue on through the nephron, where it can either be reabsorbed elsewhere, or if it's glucose, there will be no more transporters and they will be excreted from the blood. Now, this is important when we talk about a condition called diabetes mellitus. Diabetes means excessive urination, because glucose is actually highly osmotic and it will actually keep water into the nephron. So diabetes means excessive urination and mellitus means sweet. And we know that there's two forms of diabetes, type 1 and type 2. We won't talk about those now. But what happens with diabetes is that normally the glucose that is present in the blood is going to be taken in by cells and used via cellular respiration to make ATP. But the problem with diabetes is that there's either no insulin or not enough insulin. And insulin tells the cells that it's okay to take in glucose. If there's not enough insulin, then there's not enough signals to tell cells to bring glucose into the cell. So what happens is that lots of that glucose stays in the blood, raising the plasma concentration. So if the cells are not taking in enough glucose, what's going to happen is that it's going to raise the plasma concentration, it's going to get into the kidneys, and then that plasma glucose is going to enter the nephrons. And if the concentration is too high, then it's going to end up in the urine. That's one way that doctors test for to see if patients have diabetes mellitus, is they'll give them a simple urine test. They'll give them a glucose test strip, the urinate on it, and if it tests positive, that means that glucose is present in their urine. And the only reason why glucose would be present in the urine is if there's too much glucose entering the nephron and it's exceeded the transport max. All right. Well, I hope you found this talk informative, or at the very least, slightly entertaining. And if you have any questions, you know how to get a hold of me. All right. See you all soon.